use of dilatometer to screen refractory raw materials. Very common thing which we are facing right now. COVID shutdowns, freight cost increase. You can see the freight cost has increased so much. And this is like a bit older graph, so like the present cost is like somewhere here maybe. Raw material shortage. So the main thing which we are facing right now, the refractory industry, and speaking on their behalf, though I'm a student still, is that we are facing a lot of fluctuation in quality of the raw materials. And right now, like due to the circular economy, we want to recycle materials, use reclaimed materials from the steel plant, which has impurities which are somewhat different from what we find naturally. So let's say you have an impure clay or an impure bauxite, it has certain impurities. But if you get a used slide gate plate from the steel industry, that has a different set of impurities. And the liquid phase it forms as a result of it is different. So we are facing like a situation which is unprecedented. And so what we face right now is that we have like a different raw material. Let's say we want to try a reclaimed matte carbon brick from a certain steel plant, and we want to try it. And we know that it's inexpensive, and we are like trying to make more cost-effective refractories, but we are not really sure about its quality. And so this talk is about that. Like how can we deal with like this fluctuation in refractory raw material quality, and do we have a better method to screen them? Because normally what we do is that we have this new raw material which looks attractive, we see its test certificate which looks good, we make some production batches, 2 to 20 tons, whatever the case, test porosity and CCS, and it is not that bad. We dispatch it to customer, and a few months later we find out, and we then try to look back and see where we messed up. The second alternative, which is a better one, is that we make smaller batches, we test the properties, then we make larger batches. If the properties are good, we do more exhaustive studies like XRD, and then if the properties are good, we go for production. So this is like the long method, this is the short method, but the risky method. The third alternative, which I am proposing, is we run dilatometry on the raw materials itself, and we see if it is matching with the standard material, and then if it is, then we make production batches and test the qualities, and then we send it to the customer. So this is kind of like in between, but it's closer and much faster. And since you're doing dilatometry, you get kind of like a gauging the hot properties of the material, the raw material in this case. So before going into how we use the dilatometer, let's first talk about like the dilatometer itself. So what I've learned from life of a PhD student, we try something, we see that we make mistakes, and then we go and fix it. And that's what this story is about. So magnesium titanate aggregate, when I first measured it, I saw that this expansion coefficient does not make sense. And then I found that we need to do a calibration of the machine itself. And that's how we get like better data. So how do we calibrate it? So this is like a zoom in view of this. You see the thermocouple around there, this is the push rod. And these are two alumina spacers, 2 millimeter thick and 10 millimeter in diameter. And these are like the end blocks. So this was typically designed for a 50 millimeter sample, but our samples were thinner. So we had some spacers in between. So what we do is that first we run the dilatometer without any samples, so just the spacers, and we get the data. And then we use that data to correct or calibrate this raw data, and that's how we get very accurate thermal expansion coefficient or dilatometry data. So when we do for sintering studies, we place a pressed pellet sandwiched between these two spacers. We do the dilatometry, and this is how it looks like after the test. You see that it has shrunk due to sintering. So what are like the best practices which I've learned from this experience is that, and this is again published already. So those aluminum spacer calibration, you see like it's perfect straight line. we got a R-squared value of 0.996, which is pretty good. So what happens is that when you correct it, you get like very accurate thermal expansion coefficient. And when you do the dilatometry of your pressed pellets, you can see things like magnesium titanate, which is of Spinel formation, or you can see like differences in shrinkage values of alumina with different impurity content. But make sure that you're doing the test in a vibration-free environment and you're not allowing any loose powder to react with the alumina spacers here. So if you like, make sure to clean these spots because you can like, corrode your dilatometer and you can get like sticking or vibration and this causes errors like these. The second is that make sure you're doing this calibration run at the same temperature, heating rate and dwell time as your actual test. So there are 3 examples here. So this is like the corrected value at 5 degrees Celsius per minute. And when you give like a 2-hour soaking time, you see like the data is way off. Or if you do a faster heating rate and calibrate it at a lower temperature, again you see a difference in values. So this is like an equipment which you need to pay close attention that you are calibrating it right. Otherwise you will get data which will not make any sense. Now, coming back to the raw materials thing. So we get raw materials with different particle size, impurity content, and tap density. So this is like the first example. So what you see here is that, first off, this is tabular alumina, fines, and then calcined alumina, and then this is some alumina from the lab, and this is reactive alumina. You see that there is a clear difference in the sintering temperature of these 3 materials. And obviously the lower particle size sinters faster. Again, what you see here is that you have DBM here, and you have Spinel, and interestingly, this Spinel is made from this calcined alumina and this MgO. And when you combine these two, you see that there is no shrinkage. Whereas the Spinel, which is preformed from these 2 materials, it is sintering much faster. So dilatometry can help you. So let's say you got this calcined alumina from some supplier and you see that it is inexpensive. Better run a dilatometer and see that if it is matching with your actual, like good quality material, like say from Almatis, whether it is like matching the actual material. The second thing is that if your raw material has impurities in it, so what happens is that this red curve is the pure alumina, like the alumina without any impurities, and it is like 99.5% pure. And then this alumina has some added impurities. I added B2O3 and TiO2 just to simulate a used slide plate from the steel industry. So, it will obviously have some iron impurities which will form liquid phase in it. And what you see here is that not only you see that this is shrinking at the same temperature, let's say 1400 degrees Celsius, the shrinkage is much higher, meaning it is sintering much faster. If you do a derivative of this versus the x-axis, which is temperature in this case, you see that the pure alumina, the peak of this is higher than 6050, whereas with only 1% impurity, the peak temperature is 1460. And for 2% impurity, you see 1430. So what you see here is that just with 1% or 2% impurities, the sintering temperature, the optimum sintering temperature is shifting so much. So this is a simple test to do. Just press one pellet and put it in a dilatometer, and this is just like you can do it in Excel, and you can calculate that, okay, we see like a difference in the peak temperatures. And that should tell you, okay, that this raw material from certain company is actually shrinking much faster, and maybe there is a lot of impurity in it, and we should not go for this material. So again, dilatometer is like giving you a fast test to screen raw materials with different impurity content. Second, tap density. We all know tap density gives a measure of the powder packing density, and refractories have different particle sizes. We add them in certain ratios. This is from a very fundamental work. What you see here is that as the coarse to fine particle size ratio increases, the porosity in the mix decreases. That means the density is increasing. Also what you see is that 70s to 30 around this point, you get the highest density, meaning the lowest porosity. So we all know like tap density is a function of like particle size distribution, but moreover, it is also a function of the sphericity of the particles. So if you have like angular particles, you will have higher porosity, meaning lower tap density, and if you have spherical particles, it will pack well, and you will have lower density, lower porosity. So maybe you do a screen analysis and you are seeing that the screen analysis of the reclaimed raw material is matching with your like good raw material, but since the particle shape is not the same, you will end up having a difference in particle in the tap density. And when you do dilatometry, this is just like a simple dilatometry centering shrinkage. This is the low tap density material and the high tap density material. You don't see any difference, but if you just do some quick math on it, so rho g is the green density, and you express this as a fraction of the true density of the material, which is 3.98 for alumina. So you get a percentage. So you see that the good quality alumina has say 56% green density, whereas the low tap density alumina, let's call it the reclaimed material, has 53% density. And though there is just like a 3% difference in the green density, you see that the difference in the fired density is 5%. And all you are doing is that you are using this dilatometry raw data and you are converting it into a fraction and just adding 1 to it and dividing this green density by this fraction's cube. So it's very simple test. You can do it in Excel and you can get the density in just one test. So normally what people do is that take the raw material, fire it at 1400, fire it at 1500, fire it at 1600 and measure density here. Here you are doing just one test and you're just getting the full temperature range, the density values. Again, a fast, easy technique to screen raw materials. Now the second thing is that, let's say you do XRF and you see that the chemistry is same of the raw material, but it has some difference in mineral content. I will go for the example of magnesium titanate, but before that let me explain why magnesium titanate. So first thing you are seeing here is that this is a in situ magnesium titanate forming brick with some in situ spinel, and as the titanium content is increasing, it is forming more and more Mg2PiO4 and the porosity is increasing. And we all know as the porosity goes high, the strength goes low. But what you see here is that the hot memory is not changing at all. What this means is that why is this so? This is in the this is because this spinel is going into a solid solution with this magnesium titanate phase, and they have like complete solid solution, and that's why it is giving bonding in the aggregate matrix is bonding well, and you are getting high hot MR despite the high porosity. The second thing which this magnesium titanate material does is that it can form a slag barrier coating. So when your slag is interacting with your refractory at this junction point, it forms this calcium titanate phase, which is a refractory phase, and it prevents slag corrosion. And we have actually taken some sample out of it and did XRD, and we found this calcium titanate peaks in it. So this material is actually, it does work in real life. And there are like a few patents and 1 or 2 research papers which talk about this. So how do we make, so as you see, like you are getting so much high porosity, like say 30% in the break, so we don't need that much porosity. So in order to reduce the porosity, you need preformed magnesium titanate. So this slide is telling you how to make preformed magnesium titanate. So what you are seeing here is that lab grade MgO, lab grade TiO2, but 2 different TiO2s. One is rutile, one is anatase. And rutile is denser than anatase. So what happens is that when you form this in situ magnesium titanate, there is a volume expansion of 9% for rutile and only 4.5% for anatase. And you see that there is a difference here. So the rutile is expanding more than this anatase. Not only that, if you do a derivative of this red curve is a derivative, you see that the rutile phase is actually, this magnesium titanate formation is at a higher temperature, and also the sintering is at a higher temperature. So anatase not only gives you lesser expansion in the magnesium titanate formation, it also sinters faster. So the second thing what you see is here is that this is made from industrial raw materials. So I used DBM and then industrial rutile, and I reacted them together. And the same crystal structure difference, rutile and anatase, you see this big difference. You see 7.2% expansion for the rutile-based magnesium titanate and only 1% expansion for the anatase-based Mg2TiO4. So this difference is huge, 7% versus 1%. So if you can reduce the expansion from 7% to 1%, naturally you can control this porosity formation. So this anatase gives you like a raw material which you can use for in situ magnesium titanate formation, which will be inexpensive. And if you want to make preformed aggregates, you can do that, and anatase again would be the way to go forward. And you end up having like higher density, and this rutile, what you see that is that you can get 0% porosity for anatase, but 4% porosity for rutile. So this was some preliminary work, as I told, that magnesium titanate forms this high porosity if you add too much content. Here, this much, I think it was like 30% magnesium titanate formation in the brick. You see all this porosity in it. What you also see is that this magnesium aluminate spinel is forming, and it has 7.6% expansion, whereas the magnesium titanate has 3.3% expansion. And let's say you want to make a brick containing both of them. So it's better to add both of them together in the raw form. So you add MgO, Ar2O3, and TiO2 in the matrix, and what you see here is that this expansion is less than either of them. And also what you see here is that the sintering temperature, which is the shrinkage temperature here, is much lower than the spinel. So the blue curve is the spinel. The peak temperature is, like the peak is even going further than 1600 degrees C, whereas the red, which is the mix of this magnesium titanate and aluminum, magnesium titanate and magnesium aluminate in the raw form, you see that it's sintering at a lower temperature. So dilatometry again is telling you that if you want to in situ magnesium titanate and magnesium aluminate forming refractory, if you want to make that, it is better to add these raw materials in the matrix itself, and it can give you a lower total expansion and as well as lower sintering temperature. So your brick or castable will be better. And finally, forming like in-house inexpensive reactive spinel or black powder with high sinterability. So the idea is that, let's say you have a customer where the profit margin is not that high, and you want to make something in-house. Some spinel, you cannot buy the premium grade spinels which is available in the market. You want to make something yourself, and this test is showing you at what temperature you should do. So normally when you look at a spinel paper, you see this curve, this expansion due to spinel formation, in situ spinel formation. You see that it's like 8% expansion, around 1400-1500 degrees Celsius. The big question is, at what temperature should you fire your spinel powder in order to ensure that it has formed spinel completely, there is no unreacted MgO and Al2O3? Do you fire it at 1485? So this is the derivative curve. You see that the expansion starts at 1050 and then its peak as it is at 1150. So do you do it at 1050? Do you do it at 1150? What temperature do you do? How do you know that it has formed without doing XRD? So this is a dilatometric step scan. Simple, just you feed a firing rate in it so that it has this kind of steps. So 1100 degree, 1 hour soaking, 1200, 1 hour soaking, 1300, 1 hour soaking, and so on. And what you see is that the brown curve is the expansion curve. So at 1100 it's expanding, then 1200 again expanding, 1300 again expanding, 1400 it stops. So this, since spinel is an expansion, like it has expansion during its formation, so what you can see is that without doing XRD in just one single test, you can tell that expansion ends at 1400 degrees C. So this is the temperature at which you should fire your spinel powder. Now you can combine this with any grade of DBM, any grade of calcite or reactive alumina, and you can find appropriate temperatures easily in just one single test. And then we have confirmed this. We took this powder 1400 degrees C 1 hour, and we did XRD, and we saw that it is single phase spinel without any unreacted magnesia or unreacted alumina in it. Second is an example of zinc aluminate. So this is our upcoming paper. We're going to submit in a few weeks. So what you see here is that zinc aluminate formation from industrial zinc oxide, which is from US Zinc, and then reactive alumina from Almatis. What you see here is that the zinc aluminate formation, like again, it has similar expansion with as compared to magnesium aluminate spinel, and the peak expansion is at 1000 degrees C, meaning the reaction is fastest at this, and then it also sinters by 1350. So when you do a dilatometric step scan, what you can see is that if you calcine this powder mixture at 1050 degrees C for 1 hour, it completes this zinc aluminate formation. And we confirmed this with XRD. It was a single phase zinc aluminate, no unreacted zinc oxide, no unreacted aluminum oxide. So this dilatometric step scan is again confirming that just run one single test and you get to know at what temperature you should calcine your material in order to form a phase. It can be molite, because molite again expands just like spinel or zinc aluminate. Now why zinc aluminate like all of a sudden? So zinc aluminate, one thing is that it bonds very well with alumina and spinel. You see this is alumina, this is zinc oxide, this is the zinc aluminate spinel. You see this solid solution range. Not only that, if you mix it with magnesium aluminate spinel, it has complete solid solubility. So as you know, like macron spinel has a complex spinel formation, like iron chromate and magnesium chromate all bonding together. So if you add magnesium aluminate with zinc aluminate, again you get like very good bonding. That can give you a very high hot amount. This is recent papers from 2 different groups. What you see here is that a tabular alumina castable, they are adding basic zinc carbonate, which is zinc oxide, zinc with hydroxide and carboxyl ions in it. So just with 1% zinc aluminate formation, the hot amount is increasing so much, like 2 times almost. Second thing, what you see is that this is this blue curve has magnesium aluminate and zinc aluminate. The total quantity is 22%. What you see is that early stage strength development. You see after 1100 the strength is increasing. So this is all due to this solid solution between these two phases which I talked about earlier. So we all know that in castables, the low temperature strength is a thing of concern. The castable is very weak in this temperature range. And if you can increase the temperature, if you can increase the strength of the material at a lower temperature, it is going to benefit in your, like castable strength development. So again, not only hot MOR, zinc aluminate is also very good for iron with slag. Even it's better than zirconium oxide. So what you see here is that zirconium oxide, iron oxide phase diagram, you see the eutectic at 1525, whereas for zinc aluminate, zinc oxide and Fe2O3, it is 100 degree, almost 90 degrees Celsius higher. So again, zinc aluminate is like very good against FeO with slag. Similarly for FeO, even more corrosive than Fe2O3. So 3030 is the eutectic temperature for zirconium dioxide, whereas for zinc oxide there is no eutectic at all. So it's even higher than like 1370 or something. So zinc aluminate could be the next good refractory, emerging refractory. Finally, dilatometer. These are dilatometer run on the aggregates themselves. So you see fused magnesia has a highest expansion coefficient, much more than DBN, just because there is like crystal size difference in it. You see fused macrome's expansion coefficient, and then you see tabular alumina, spinel, and zinc aluminate all almost the same. So this is one of my previous paper in JSORS. What you see here is that this magnesia spinel braid had a very good thermal shock resistance. Why? Because these are the fused NGO grains, the periclase grains, and you see fracture porosity around it. Why? Because the matrix is a mixture of magnesia and spinel. Now, you see here is that spinel has a lower expansion coefficient. So due to this expansion coefficient mismatch, it is creating gaps around the high expansion phase. So whatever expands more, contracts more during cooling, right? So you see these gaps around here, and these thermal shock induced cracks get attenuated in this fracture porosity around these NGO grains, and that's how you get high thermal shock resistance. You can do the same thing with zinc aluminate containing refractories. You can combine it with NGO, and you can get a similar thermal shock resistance. And as I mentioned earlier, zinc aluminate has more corrosion resistance, so you might actually get very good refractories with both thermal shock resistance and corrosion resistance at the same time. Again, this curve like tells you that fused magnesia has an expansion coefficient around 17, DBM is around 16, Macrome is around 13, whereas the spinels and tabular alumina, these are all close to this 10, around that range at 1600 degrees C. So in conclusion, like dilatometry is a very fast method to screen suspicious and inexpensive raw materials. It eliminates the need to fire samples at different temperatures or perform multiple XRD. It can help you select between what polymorph is better even though they have the same chemistry. It can tell you from the peak temperatures that more liquid phase or less liquid phase is present in the raw material or not. And more importantly, the dilatometric steps can help you in like forming reactive spinel without any unreacted raw materials in them. So in a nutshell, like dilatometry can really accelerate your R&D trials. So with that, I would like to thank ASO's Refractory division for funding this trip, as well as my university, and funding from UAE for the Zinc project, and also ASTM for giving me scholarships for my teaching. So, thank you. Questions? Yes, please.
Thanks, it was a very good presentation. Just a quick question. Like when you're testing raw materials, when you receive them, they have a range of chemistries.
Mm-hmm.
So when you're doing the test, let's say you have 98% of aluminum compared to 97 or 99.
Right.
So you have a range.
Right.
So what's the tolerance you have when you're running those tests?
So,
Is you're not expecting all the raw materials coming in the same chemistry.
right. So normally what happens is that if you buy a suspicious raw material, right? So there is batch to batch variation. And like say one bag of 1,000 tons is like different, sorry, 1 ton is different from another bag. So the best case scenario would be test from each bag, just as you do in a normal test. If you ask that, is there any variation between, say if you want to repeat this test, do you get the same data? Yes. So let's say at 1400 degrees C, you see that there is like around 5% shrinkage is there. So if I repeat this test from if it is chemistry wise, if it is similar, then I will get 5%, 5 plus minus 0.1%. So the test itself is very repeatable. But if your bag of raw material itself is not consistent, that's what this test is telling you, that it is not consistent. This is a screening technique. So you can rely on the test, and it gives you a measure of the inconsistency of the quality of the raw material. Yes. It is repeatable. That's what it is.
So, quick question. For those tests, what kind of sample you are using? How you make sample? You just use powder, or you make this?
So this is the sample. This is a pressed pellet, 10 millimeter diameter and 3 millimeter thickness. You should keep the thickness constant.
So
because
you think the way how you press this pellet will be affected the result?
Yes. So let's say here your variable is the raw material chemistry or the raw material particle shape. So you want to make your samples in the same way. Let's say you're running XRF. If you want to make those pressed pellets and you do XRF, you want to have that same consistent procedure, right? Likewise, you need to press your pellets in the same way with PDA binder or whatever binder you choose to use, and in the same mold. The sample dimension is fixed with this dimension of the dilatometer itself. If you buy a larger diameter dilatometer, you can use a larger sample.
So do you think when you prepare sample, you need to also consider about the application? Because for the here you are only test pure raw material.
Correct.
But if you are using any castle or any carbon for refractories, you are only using maybe 20% or 30%. So maybe the fact is shown here, if you mix into your real refractory, maybe the activity will be very small.
Right. So what happens is that that's actually the very castable and it has 10% of a certain grade of aluminum oxide, and you want to try another different grade of aluminum oxide, 10%, you want to replace it. What normal people do is they replace that 10%. But you don't know what this 10% new alumina is interacting with the other things in the composition. So the big question is this alumina same as the alumate alumina or whatever different alumina is? So this test is just focusing on the raw material itself. So if you get the same 5% shrinkage of the premium raw material versus your new raw material, then you can realize, okay, our raw materials are in the same page. So now we can make some final compositions and test them. But you just throw your raw material in the big formulation, it has microsilica in it, it's fumed silica, you don't know what it is reacting with. So that is why I'm doing it. Now coming to your big question, like how does it tell the final properties of the brick or castable, because this is just one raw material. So I have come to know by after talking with other people that there are in fact bigger dilatometers in place where they test like thicker samples. So you can put like, instead of this thin push rod, it has a thicker push rod, it has a bigger sample chamber, so you can actually fit like a cylinder of this size and test your actual castable or the brick sample itself. But again, like whenever we fire bricks or castables, we limit it to plus minus 1 or 2% expansion contraction, right? So you won't see that much difference. Again, you see this raw material. Look at this y-axis. This is like 14%. This is like 6%, 7% changes. You need to magnify your y-axis to see the changes of the raw material. That's why doing this test separately for individual raw materials, and then probably you can buy a bigger dilatometer and put your castable or brick directly in it and see how do they interact. It's just like one test kind of trying to replace other tests. Again, it cannot replace completely XRDs. XRD is going to give you phase composition for sure. But let's say you are a startup company or some company does not have an XRD on its own. What do? Then you can use this method as like one shot, like multi-purpose testing facility, you can say. Because you can put in the expansion curve which I showed here, this fused MgO, this is actually I got like a sample and I polished in like silicon carbide paper and put it in the dilatometer and measured the fused MgO's expansion coefficient. This is usually not reported. But once you have that data, you can use it for finite element simulation and predict the thermomechanical performance of your bricks. Or you can use it to just like we designed a thermal shock resistant refractories using that. So like studying the raw material actually can give you like bigger control over your end properties of the refractory. So I guess like yes.
Just a quick question. In your one slide, you show the calibration.
Yes.
If you're testing MgO-based, like MgO sample, and you use alumina spacer,
Right.
is there any concern on any reaction?
Right.
To have effect on the results?
It does. So if I have alumina sample like calcined or Spinel sample, you can use the same spacer for 10 cycles or 15 cycles. But when you use MgO, you can only use it for 3 or 5 cycles. After that, you see that the spacer has some reaction on it, and also you see these things in the data. This is all due to sticking samples or vibration. So you will know that your sample is reacting with your spacer. So it works. It does not affect a sample because most of these tests I run, since I'm a PhD student, I need to be repeatable. That's what my advisor wants. So I have done 2 or 3 times each test, and I see that it is repeatable. Yeah. Again, like you can buy these spacers. These are not very expensive, so you can buy them easily. And like we used to buy like 50 spacers at a time, and then run a lot of tests. So, any more questions? Yes.
So you mentioned that the thickness has to be very precise, around 3
Yes. So 3 millimeters, like you can have 2 millimeters, you can have 1 millimeter. Doesn't matter. But if you choose 1 millimeter, be 1 millimeter in all of your samples. Why? Because this shrinkage value, if you so what is the shrinkage value? It is the change of your thickness as a function of temperature. So if you have a thicker sample like this, and if you have a thinner sample, this thicker sample will shrink more. Even if you are doing a percentage, it does shrink more. And I've done it. I've done 2 millimeter samples, 3 millimeter samples. And as soon as I saw like, man, this is different. We are not in the same page. So I said, okay, my own internal standard is 3 millimeter, but you can have a different one. Again, like, very good point, like, getting consistent data from this, as I said, like, the repeatability is like 5%, 5.05%. You get those by doing these small things in the test method itself. That's why like ASTM has this standard test method. There is none for dilatometry for this kind of thing, but we might in future.